This presentation reports the scope, methods, and principal findings of a literature review on cognitive development in mechanical and civil engineering. The review covers research from 2000 to 2005 with selected early foundational studies and is organized around four cognitive domains. Why it matters. Engineering problems tend to be ill-defined, requiring independent goal setting, constraint identification, and solution generation. Such tasks generate high cognitive demand. Understanding how cognition changes from novice to expert clarifies why some educational and workplace practices succeed while others don't. The literature is grouped into four categories that were recurring themes in the research. These categories are problem-solving strategies, metacognition, knowledge integration, and cognitive load management. Main difference between novice and experts in problem-solving strategies is that experts typically invest more time in problem representation and use forward-working plans derived from basic principles. Novices, on the other hand, rely on backward reasoning, trial and error, and surface cues. Time on task evidence indicates that experts allocate roughly twice as much initial effort to framing and correspondingly less to later rework. Metacognition refers to planning, monitoring, and regulating one's cognitive processes. Lawanto's 2010 study followed 168 senior engineering students through semester-long capstone projects. They monitored cognitive self-appraisal and cognitive self-management in students throughout their projects. The main findings here is that students who had higher scores for these metrics performed better in their projects. Interestingly, these scores for self-appraisal and self-management improved throughout their projects, indicating that these are skills that can be learned and improved on. Integrated knowledge links concepts across topics and experiences. Shee's study from 1981 asked experts and novices to sort 24 mechanics problems. Experts grouped 77% of them by deep principles, such as Newton's second law, energy conservation, momentum, while novices only did so for 31% of the problems. The outcome implies that experts possess principle-centered schemas, whereas novices rely on superficial similarity. Instruction that emphasize underlying principles may accelerate schema formation and lead to expertise more quickly. Cognitive load theory separates mental demand into intrinsic load, which is the task complexity, extraneous load, which is presentation induced, and germane load, which is the schema construction. Effective instruction minimizes extraneous load and supports germane load with the learner's capacity. Chase and Simon showed that chess experts recall about 4 times as many pieces as novices when positions reflect the real games, but they showed no advantage with random layouts. The results indicate that superior performance stems from domain-specific chunks that compress information, not from greater general memory. With these findings, we can come up with some recommended instructional practices. These are that it's important to provide an explicit, repeatable problem-solving routine early to students. Institutions should require short reflection notes after tasks to enforce metacognition. Design assignments that compel students to link concepts across courses have also been shown to be useful. And CLT principles, like beginning with worked out examples and gradually fading out the guidance and avoid unnecessary detail in instructional materials, have been found to help. In the professional side, organizations should take the following measures. They should pair less experienced engineers with mentors to explain their reasoning aloud. They should construct post-project reviews that examine underlying assumptions and thought processes. They should supply micro-learning modules that enforce core schemas, and use tools to offload routine calculations and other repetitive work. In conclusion, expert engineering performance is characterized by structured planning, metacognitive regulation, principle-centered knowledge networks, and efficient load management. Deliberate curricular scaffolds, workplace mentoring, and longitudinal research can shorten the novice expert trajectory and improve outcomes in mechanical and civil engineering practice.